In the 5th century before the Common Era, a Greek philosopher named Zeno of Elea proposed a simple challenge: walk across a room. Before you reach the far wall, he said, you must first cross half the distance. Before you cross that half, you must cross half of the half, and before that, half again. If space can be divided infinitely, Zeno argued, you can never actually begin moving at all. Tonight, we will unravel paradoxes that haunted mathematics for 2,000 years and still unsettle philosophers today. We will meet a man who crafted arguments so elegant and disturbing they have never been fully resolved, weapons in a metaphysical war that began in an ancient Greek colony and echoes still in quantum physics laboratories. We will trace how these puzzles about arrows and tortoises forced humanity to confront infinity itself, to question whether mathematics describes reality or merely approximates it, and to wonder whether motion, the most ordinary fact of existence, might be impossible to explain. From Aristotle's frustration to Georg Cantor's revolutionary infinities, from Isaac Newton's calculus to the strange implications of relativity and quantum mechanics, these ancient riddles have shaped the entire history of thought about space, time, and the nature of existence. Zeno of Elea was born around 490 before the Common Era in a Greek settlement on the southwestern coast of what is now Italy. Elea was a prosperous port far enough from Athens to develop its own intellectual traditions, close enough to the currents of Greek thought to matter. The world Zeno inhabited was experiencing an unprecedented explosion of ideas. Philosophers across the Greek-speaking world were abandoning mythological explanations and attempting to understand the cosmos through reason alone. Heraclitus had declared that everything flows, that change is the fundamental reality. Pythagoras and his followers insisted that number and ratio governed all things. In this ferment of competing visions, Zeno became the devoted student of Parmenides, an older philosopher from Elea, who made perhaps the most audacious claim in the history of philosophy, that change, motion, and multiplicity are illusions. According to Parmenides, reality is one unchanging, eternal, indivisible whole. What we perceive as motion and variety and transformation is mere appearance, a trick of the senses. True being, Parmenides insisted, cannot change, cannot move, cannot become. It simply is. The claim seemed absurd. Open your eyes and you see motion everywhere. Walk across a room and you have changed your location. Drop a stone and it falls. How could anyone deny such obvious facts? Critics attacked Parmenides mercilessly, pointing to the evidence of everyday experience. And this is where Zeno entered the story. He did not defend his teacher by arguing that the critics were wrong about what they observed. Instead, he showed that their own assumptions led to contradictions just as severe as Parmenides' conclusion. If you believe motion is real, Zeno argued, if you believe that space and time are infinitely divisible, if you trust your common sense about how the world works, then you must accept certain logical consequences, and those consequences are absurd. The technical term for Zeno's method is reductio ad absurdum, reduction to absurdity. You assume your opponent's position is correct, then demonstrate that it leads to impossible conclusions. If their assumptions generate contradictions, something must be wrong with those assumptions. Zeno did not necessarily believe his own paradoxes proved motion was impossible. He was showing that his critics' beliefs about motion and plurality led to equal absurdities. If you mock Parmenides for denying motion, Zeno suggested, you had better explain how motion is possible given your own premises. What made this approach revolutionary was its rigor. Zeno was not appealing to intuition or authority or poetic imagery. He was constructing step-by-step logical arguments that seemed irrefutable. Ancient sources tell us he wrote a book containing approximately 40 paradoxes. Most are lost. We know them only through fragments preserved by later philosophers, primarily Aristotle, who discussed them extensively 3 centuries later. 4 paradoxes of motion survived in enough detail to torment every subsequent generation: the dichotomy, Achilles and the tortoise, the arrow and the stadium. Each attacks the possibility of motion from a different angle. Each seems sophistical at first, a clever trick of words. Then you try to refute them and discover that you cannot. Consider what Zeno accomplished. He lived 2,500 years ago in a world without symbolic algebra, without calculus, without formal logic as we know it. He had no mathematical tools beyond geometry and basic arithmetic. Yet he identified problems that would not receive even partially satisfying answers until the development of mathematical analysis in the 17th century and set theory in the 19th. His arguments revealed that ordinary concepts like space, time, motion, and multiplicity rest on assumptions that, when examined carefully, lead to profound difficulties. He showed that infinity is not just very large, but qualitatively strange, that dividing something endlessly is not the same as dividing it a large number of times, and that our intuitions about continuity and discreteness might both be incoherent. These are not trivial semantic games. They are genuine conceptual problems at the foundation of how we understand reality. The paradoxes also demonstrate something unsettling about the relationship between experience and reason. You can walk across a room. Achilles does overtake the tortoise. Arrows do reach their targets. Experience confirms these facts beyond any doubt. Yet Zeno's arguments seem to prove they cannot happen. Where is the flaw in the logic? For 2 millennia, philosophers and mathematicians struggled to answer. Aristotle offered an explanation involving the distinction between potential and actual division of space. Medieval scholars debated whether space and time were composed of indivisible atoms or were infinitely divisible continua. Newton and Gottfried Wilhelm Leibniz invented calculus and showed that infinite series could converge to finite sums, offering mathematical tools to handle Zeno's infinities. Cantor discovered that infinity itself comes in different sizes, that some infinite sets are larger than others. 20th century physics revealed that space and time are woven together in ways Zeno never imagined, and that at the smallest scales quantum effects introduce fundamental uncertainties that might bypass his assumptions. Yet even now, even after all these developments, philosophers debate whether Zeno's paradoxes have been truly solved or merely sidestepped. What emerges from this long confrontation is a profound question about the nature of explanation itself. We can calculate with extraordinary precision how long it takes to cross a room. We can predict exactly when Achilles will overtake the tortoise. But can we explain in a logically rigorous way that respects the infinite divisibility of space and time how these motions actually occur? Zeno forces us to distinguish between practical solvability and conceptual understanding. The mathematics works. The predictions are accurate. The engineering succeeds. But does that mean we understand what is really happening when something moves through space over time? Or have we simply developed very sophisticated techniques for navigating around problems we have not actually resolved? These paradoxes endure because they touch something fundamental about the limits of human reasoning when confronting infinity and continuity. They remind us that the universe does not necessarily operate according to principles our minds find comfortable or our language can easily express. They suggest that the gap between mathematical models and physical reality might be deeper than we typically acknowledge, and they demonstrate that ancient philosophers, working with nothing but careful thought and logical analysis, could identify problems that remain unsettled after 25 centuries of intellectual effort. Zeno's arguments are not historical curiosities. They are living challenges, questions that each generation must face again, with new tools and new insights, only to discover that the problems resist final solutions. Understanding why these paradoxes were created, how they work, and why they have proven so durable reveals something essential about both the power and the limitations of human thought. We begin with the man himself, the context that produced him, and the philosophical war in which his paradoxes served as weapons. Only then will we be prepared to encounter the arguments directly, to feel their force, and to trace their strange persistence through the centuries that followed. The colony of Elea stood on the western coast of southern Italy, a Greek settlement clinging to limestone cliffs above the Tyrrhenian Sea. In the middle decades of the 5th century before the Common Era, this remote outpost became home to a school of thought so radical that it seemed to deny the evidence of every human sense. Walk through the agora, and you appeared to be moving. Watch the sun arc across the sky, and change seemed obvious. Yet the philosophers of Elea insisted that all of this was illusion. Reality, they claimed, was a single unchanging whole. Motion was impossible. Plurality was incoherent. What you saw with your eyes was not what existed in truth. This was the world into which Zeno was born, around 490 before the Common Era. The details of his early life have dissolved into time, preserved only in fragments and later testimonies. We know he became a devoted student of Parmenides, the founder of the Eleatic school, and that the relationship between teacher and student was close enough to inspire rumors. Plato, writing more than half a century after both men had died, suggested in his dialogue Parmenides that the two shared not just intellectual but romantic bonds. Whether or not this was true, the philosophical devotion was unquestionable. Parmenides had proposed a vision of reality so counterintuitive, so opposed to ordinary experience, that it invited immediate ridicule. Zeno made it his life's work to defend that vision. Parmenides had written a philosophical poem, composed in dactylic hexameter, like the epics of Homer, in which he described a journey to meet a goddess who revealed the truth about existence. The goddess explained that reality could not be multiple, could not change, could not come into being or pass away. To exist meant to exist completely, timelessly, unchangingly. If something could change, it would have to become what it was not. But what is not does not exist, and therefore cannot be invoked in any explanation. From this stark logical foundation, Parmenides concluded that all apparent motion, all plurality, all transformation was mere appearance, the senses deceived, opinion misled. Only reason could grasp the truth, and reason declared that all was one. You can imagine how this claim was received. The critics did not lack for ammunition. If reality is one, why do we perceive many things? If motion is impossible, how do we walk? If change is illusion, what accounts for birth and death, growth and decay, the manifest transformations occurring constantly around us? Parmenides offered abstract logical arguments, but his opponents could point to the entire world as counter-evidence. The Eleatic philosophy seemed absurd on its face, the product of reasoning that had lost touch with reality. Zeno stepped into this conflict, not as a neutral investigator, but as an advocate. According to Plato, he wrote a book in his youth containing approximately 40 arguments, all designed to defend Parmenides by attacking his critics. The book itself has been lost. What survives are fragments and descriptions preserved by later philosophers, particularly Aristotle, who discussed several of Zeno's arguments extensively while trying to refute them. From these scattered sources, we can reconstruct both the structure of Zeno's reasoning and his strategic purpose. He was not claiming that motion was impossible because he believed it was impossible. He was demonstrating that if you accepted certain assumptions about space, time, and plurality that seemed obvious and uncontroversial, you would be forced to conclude that motion was impossible. Since you did not accept that conclusion, you should reconsider your assumptions. This method of argument, known as reductio ad absurdum, was not entirely new, but Zeno wielded it with unprecedented precision and power. Take your opponent's premises, follow their logic rigorously to an absurd conclusion, and thereby prove that something in the initial premises must be wrong. The beauty of this approach was its economy. Zeno did not need to prove Parmenides correct. He only needed to show that the alternative positions led to contradictions. If critics claimed that many things exist, Zeno would demonstrate that this assumption generates logical impossibilities. If they insisted that motion occurs, he would show that the very concepts of space and time they relied upon made motion incoherent. The burden of proof shifted. Parmenides might seem to contradict experience, but at least his position was logically consistent. The common-sense view, which seemed so obviously true, collapsed under scrutiny into paradox and absurdity. This was revolutionary not merely as a philosophical tactic, but as a transformation in how arguments could be conducted. Before Zeno, philosophical debate often involved competing appeals to experience, tradition, or intuitive plausibility. Zeno demonstrated that pure logic, applied with rigor and precision, could force opponents into corners from which escape seemed impossible. He showed that mathematical reasoning about space and time could generate results that defied expectation. He proved that what seems obviously true might rest on conceptual foundations too weak to support the weight of careful analysis. The intellectual climate of pre-Socratic Greece made this intervention particularly potent. The 6th and 5th centuries before the Common Era witnessed an explosion of competing cosmological theories. Thales proposed that water was the fundamental substance. Anaximenes suggested air. Heraclitus declared that everything flowed like fire, that change was the only constant. Pythagoras and his followers believed that number and geometric proportion were the key to understanding reality. Against this background of proliferating theories, each based on different assumptions about what existed and how it behaved, Zeno's method offered a kind of philosophical hygiene. If a position could not withstand logical scrutiny, if its premises generated contradictions, it should be abandoned regardless of how intuitively appealing it seemed. The specific details of Zeno's life remain frustratingly obscure. Later sources claimed he was tortured and executed for participating in a plot against a tyrant, possibly Nearchus of Elea, around 430 before the Common Era. The historian Diogenes Laertius, writing 7 centuries after the events, reported that Zeno bit off his own tongue and spat it at the tyrant rather than reveal his co-conspirators under torture. Whether this dramatic story is historical or legendary, it reflects how later generations remembered Zeno as a man of fierce conviction, willing to endure anything in defense of what he believed. But the paradoxes themselves are what survived, copied and discussed and transmitted through the centuries. They appeared in Aristotle's Physics, where the great systematizer of Greek thought struggled to refute them. They circulated among medieval scholars, who saw in them troubling questions about the relationship between mathematical abstraction and physical reality. They resurfaced during the scientific revolution, when the new physics of Galileo and Newton seemed to make them obsolete, yet somehow did not, and they returned again in the modern era, when mathematicians and physicists realized that the problems Zeno had identified were deeper and stranger than anyone had imagined. What makes the paradoxes endure is not merely their cleverness, but their ability to expose assumptions we did not realize we were making. When you think about crossing a room, you assume that space is divisible, that time passes continuously, that motion is a coherent concept. These assumptions seem so fundamental, so obvious, that questioning them appears absurd, yet Zeno shows that following their logical implications leads to conclusions just as absurd as anything Parmenides ever claimed. Either something is wrong with the assumptions, or something is wrong with our logic, or something is deeply strange about the nature of reality itself. Zeno died more than 24 centuries ago in a small Greek colony that barely appears on ancient maps. His book is lost. His biography is fragmentary. Yet the questions he formulated with such precision and economy remain alive, challenging each generation to explain what actually happens when an arrow flies or a runner crosses a finish line. He took the most ordinary experiences imaginable and revealed them to be conceptually mysterious. He showed that defending an absurd position could be easier than defending common sense, and he demonstrated that the simplest questions about space, time, and motion could resist satisfactory answers for millennia. Understanding why Zeno created his paradoxes sets the stage for encountering them directly. These were not idle puzzles but philosophical artillery, and to appreciate their power, we must see them in action. Imagine standing in a doorway. The room before you stretches 20 paces to the far wall. To reach that wall, you must first traverse half the distance, 10 paces. But before you can walk those 10 paces, you must first complete half of that distance, 5 paces, and before those 5, you must cross 2.5. Before that, 1.25. The divisions continue without end, each distance requiring traversal before the next becomes possible. Zeno of Elea observed that, if space can be divided infinitely, then between you and any destination lies an infinite sequence of smaller and smaller distances. To cross the room, you must complete an infinite number of journeys. Yet completing an infinity of anything, Zeno argued, would require infinite time. Therefore, you cannot reach the far wall. Indeed, you cannot even begin to move. This argument, known as the dichotomy, stands as perhaps the most fundamental challenge Zeno posed to our understanding of motion. Its beauty lies in its simplicity. No exotic premises, no hidden assumptions that might be questioned, only the observation that any distance, if divisible, can be divided again and again. And if this division has no natural stopping point, then the task of traversing that distance fragments into infinitely many smaller tasks. The word dichotomy itself derives from the Greek for cutting in two. Each step in Zeno's reasoning performs exactly this operation. You have the full distance, cut it in half, take one of those halves and cut it in half again. The process never terminates, because there is always another half to consider. No matter how small the remaining distance becomes, 1,000th of a pace, 1,000,000th, 1,000,000,000th, it can still be bisected. Zeno forces us to confront a question that seems to have no bottom. Where does the division stop? The ancient world had no satisfactory answer to this question, in part because they lacked a clear distinction between two different kinds of infinity. Aristotle, writing nearly a century after Zeno, would introduce this crucial division. He called one type potential infinity, the sense in which you can always perform one more division, always add one more number, always continue a process without reaching a final term. The other he termed actual infinity, the notion of a completed infinite totality, an infinite collection that exists all at once as a finished thing. The dichotomy seems to demand that you complete an actual infinity, not merely that you could, in principle, keep dividing the distance forever, but that the journey itself consists of infinitely many distinct sub-journeys that must somehow be finished. How does one finish something that has no end? The question feels like a trap with no escape. If you deny that space is infinitely divisible, you must explain what stops the division, some indivisible minimum distance that cannot be split further. Yet any such minimum seems arbitrary. Why should nature respect our inability to imagine smaller divisions? But if you accept infinite divisibility, you appear forced to accept that all motion is impossible, which contradicts the evidence of your own eyes. Zeno constructed his paradox to illuminate exactly this dilemma. His teacher Parmenides had argued that reality was a single, unchanging whole, and that plurality and change were illusions of confused perception. Critics objected that this violated common sense. Zeno's response was essentially, if you believe in many things and in motion, your position leads to absurdities just as great. The dichotomy reveals one such absurdity. Accept that distances are composed of many parts, and you cannot explain how those parts combine to allow traversal. What made this argument particularly maddening to ancient philosophers was that no one genuinely doubted that motion occurred. Zeno himself presumably walked from place to place without believing he was accomplishing the impossible. The paradox was not an assertion that motion was truly impossible, but rather a demonstration that the assumptions underlying common beliefs about motion led to logical incoherence. It was a challenge to explain how motion is possible, given that it seems to require completing the impossible. The earliest responses often involved simply denying the premise. Perhaps space is not infinitely divisible. Perhaps there are smallest possible distances, indivisible units of extension that cannot be split further. If space is composed of these minimal parts, then any journey consists of only finitely many steps from one unit to the next. Cross enough such units, and you reach your destination without confronting infinity at all. This response, though intuitively appealing, creates as many problems as it solves. What is the size of these indivisible units? Are they extended? Do they have parts? If so, why can those parts not be separated? If not, how do units without extension combine to create distances that do have extension? Add zero to itself infinitely many times, and you still have zero. Add indivisibles without magnitude together, and it seems you should still have no magnitude. The atomist solution, treating space as composed of discrete minimal units, merely relocates the mystery. Aristotle offered a more sophisticated response by appealing to his distinction between potential and actual infinity. Yes, he acknowledged, you can potentially divide any distance infinitely, But this does not mean the distance actually consists of infinitely many parts all existing simultaneously. When you walk across a room, you do not complete infinitely many discrete tasks. You perform one continuous action. The infinite divisibility of the distance is merely a fact about what could be done to it, not about what it actually is composed of. This answer has the virtue of taking Zeno's challenge seriously while avoiding the most counterintuitive conclusion, yet it leaves something unsatisfied. When you walk from the doorway to the far wall, you do in fact pass through the halfway point. You also pass through the quarter point and the eighth point and every other intermediate position Zeno identifies. In what sense, then, do those positions not exist? Aristotle's distinction between potential and actual infinity may be philosophically useful, but it does not quite explain how you accomplish what Zeno says is impossible. The problem gnawed at thinkers for centuries precisely because it seemed to permit no clean resolution. Either space is infinitely divisible, or it is not. If it is, motion seems impossible. If it is not, space seems to be made of incoherent atoms without extension. And all the while, arrows fly and people walk and the world moves on, indifferent to the logical impasse. What the dichotomy reveals, more than anything, is that our intuitive understanding of space and time rests on assumptions we do not usually examine. We think we know what it means for something to be continuous, for a distance to be traversable, for motion to be possible. Zeno demonstrates that these concepts, when inspected closely, dissolve into puzzles. The journey from here to there, the simplest act imaginable, becomes a philosophical problem of staggering depth. And Zeno had only begun. If the dichotomy makes starting motion impossible, the next paradox shows that even the fastest runner can never catch the slowest crawler. The trap tightens. The most famous philosophical puzzle in history begins with a simple sporting event. Achilles, the legendary warrior whose speed was unmatched among mortals, agrees to race a tortoise. Confident in his superiority, he offers the creature a head start of, say, 100 meters. The race begins. Common sense delivers its verdict immediately. Achilles will overtake the tortoise within moments. Yet Zeno constructed an argument proving that Achilles can never catch his slow opponent, and the proof proceeds with such crystalline logic that 25 centuries of thinkers have struggled to explain precisely where it goes wrong. The argument unfolds in stages, each one perfectly reasonable. When the race starts, the tortoise occupies a position we might call point A, 100 meters ahead. Achilles sprints toward that location. He is fast, extraordinarily so, and reaches point A in mere seconds. But during those seconds, however brief, the tortoise has not remained stationary. Slow though it is, it has advanced to a new position. Point B, perhaps 1 meter beyond where it started. Achilles has closed the gap substantially, but a gap remains. Undeterred, Achilles continues toward point B. Again he reaches it, and again the same situation emerges. In the time required for Achilles to cover that 1 meter, the tortoise has crawled forward to point C, perhaps just 10 centimeters ahead. The distance between them shrinks with each stage, but it never disappears. Every time Achilles arrives at where the tortoise was, he finds his opponent has moved to somewhere he is not. The process repeats infinitely. The distances grow smaller and smaller, but the logical structure remains identical. Reaching the previous position of the tortoise never equals reaching the tortoise itself. Zeno has trapped Achilles in an infinite sequence of tasks. He must reach point A, then point B, then point C, then point D, each one closer than the last, but none of them identical to the tortoise's current location. An infinite number of steps, no matter how small, cannot be completed. Therefore, Achilles never overtakes the tortoise. The swift runner remains forever in pursuit, approaching but never arriving, his legendary speed rendered useless by the mathematics of infinite division. The psychological power of this paradox exceeds that of its predecessor. The dichotomy argued that motion cannot begin, which contradicts experience but addresses an initial moment we might question. Achilles and the tortoise describes an ongoing process we can easily visualize, involving a competition whose outcome we know with absolute certainty. Achilles does overtake the tortoise. We have seen countless races, watched faster runners pass slower ones, observed the moment of overtaking with our own eyes. The conclusion is absurd, yet the reasoning appears flawless. Each step in Zeno's argument seems unassailable. Is it true that when Achilles reaches point A, the tortoise has moved to point B? Yes, undeniably. Is it true that reaching where the tortoise was differs from reaching where the tortoise is? Again, yes. Does this pattern repeat for every subsequent position? It does. Where then is the error? The paradox creates a strange vertigo, a sensation of being unable to locate the flaw despite knowing one must exist. Logic and experience stand in open conflict, and neither will yield. The mathematical similarity to the dichotomy becomes apparent upon reflection. Both paradoxes divide motion into infinitely many parts and declare the infinite sequence incompletable. Both rely on the idea that space and time can be subdivided without limit. Yet Achilles and the tortoise generates a different emotional response. The dichotomy presents a static, abstract problem about beginning. This paradox offers a dynamic narrative with characters, competition, and dramatic tension. It transforms a mathematical puzzle into a story, and stories lodge themselves in memory with particular tenacity. The choice of Achilles was deliberate. Greek audiences would have known him as the embodiment of martial prowess, a hero whose speed and strength were sung by poets. To render such a figure impotent, forever chasing a creature synonymous with slowness, created a vivid absurdity. The tortoise, plodding and unheroic, becomes untouchable through the power of logical argument alone. The reversal is almost comical, yet the comedy carries a philosophical sting. If logic can deny what every observer sees plainly, what trust can we place in reason? Zeno wanted his audience to feel this discomfort. The paradox was designed not merely to present a problem, but to create an experience of intellectual crisis. You watch Achilles win the race. Your eyes report this fact without ambiguity, yet you cannot identify the flaw in an argument proving the victory impossible. One of two things must be true. Either your senses deceive you about the fundamental nature of motion, or human reasoning breaks down when confronting infinity. Neither option provides comfort. The paradox reveals something profound about infinite series. Though Zeno lived long before mathematics developed tools to handle them rigorously, the distances Achilles must cover form a sequence: 100 meters, then 1 meter, then 10 centimeters, then 1 centimeter, and so on. Each distance is smaller than the previous one, shrinking according to some ratio determined by the relative speeds of racer and tortoise. The number of distances is infinite, but their sum is finite. This sum represents the point where Achilles catches his opponent. Ancient Greek mathematics had no framework for understanding how infinitely many numbers could add to a finite total. The concept seemed contradictory. How can endless addition yield a limited result? Without techniques for evaluating what later mathematicians would call convergent series, Zeno's contemporaries possessed no rigorous response. They could assert that the infinite sum must be finite, but assertion is not explanation. The gap between practical observation and theoretical understanding remained unbridged. This gap gives the paradox its lasting power. Everyone agrees Achilles overtakes the tortoise. The question is not about the physical outcome, but about the adequacy of our conceptual tools. Can we describe overtaking in a way that satisfies both logic and mathematics? Can we explain what happens when infinitely many events occur in finite time? The paradox forces us to recognize that ordinary motion, the most familiar phenomenon in human experience, becomes strange and problematic when examined with philosophical precision. The contrast with direct experience creates a peculiar tension. We navigate space constantly, moving from place to place without difficulty or confusion. Motion seems perfectly natural until we begin thinking carefully about its structure. Then familiar actions become mysterious. The same process that carries you across a room contains infinitely many stages, infinitely many moments, infinitely many positions. You complete infinite tasks every time you stand up. How is this possible? Zeno offers no answer, only the question posed with such clarity that it cannot be dismissed. The elegance of the paradox lies in its simplicity. No elaborate assumptions, no complex terminology, no appeal to obscure principles. Just a swift runner, a slow tortoise, and the observation that reaching where something was is not identical to reaching where it is. From these modest elements, Zeno constructs an argument that has occupied some of the finest minds in human history. The tortoise inches forward, Achilles sprints behind, and the gap between them becomes a window into infinity itself. These first two paradoxes assume motion is at least possible, but Zeno had an even more disturbing argument that at any single instant motion itself is incoherent. Picture an arrow in flight, frozen at a single instant, suspended in the air between bow and target. What are you seeing? The arrow occupies a precise location in space, no more and no less than its own length. It sits within an exact region, filling that space completely. Now ask yourself at this singular moment, this instant without duration, is the arrow moving? Zeno would say it cannot be. His third paradox strikes not at the completion of motion, but at its very possibility within any fragment of time. Where the dichotomy and Achilles attack the summation of infinite intervals, the arrow paradox turns its attention to the instant itself. What happens inside a moment that contains no before and no after? The logic unfolds with brutal simplicity. Consider any instant during the arrow's flight. At that instant, the arrow exists somewhere. It must occupy some region of space. That region cannot be larger than the arrow itself, for then the arrow would not fill it. The region cannot be smaller than the arrow, for then the arrow would exceed its boundaries. Therefore, at any given instant, the arrow occupies a space exactly equal to its own dimensions. But here lies the trap. To occupy a space exactly equal to itself means the arrow fits perfectly within that space, with nothing extending beyond, nothing reaching forward or backward. There is no overlap with where it was, no protrusion into where it will be. At this instant, the arrow simply is where it is. And what do we call something that is simply where it is, with no part of it anywhere else? We call it stationary. We call it at rest. The arrow at rest. Not eventually at rest, not almost at rest, but genuinely at rest at this instant. And this applies to every instant. Choose any moment during the flight, freeze time at that point, and you will find the arrow occupying exactly the space it occupies, doing nothing that could be called moving. If the arrow is at rest at each instant, and time consists entirely of instants, then the arrow is always at rest. Flight becomes impossible, not because distance divides infinitely, but because motion itself dissolves under examination. You might object that the arrow is obviously moving, that its position at one instant differs from its position at another instant. Zeno would agree about the positions, but challenge your claim about motion. The arrow exists at position A at one instant. The arrow exists at position B at a later instant. These are facts about where the arrow is, not facts about motion. Motion would require the arrow to be moving at some instant, to be in the act of traveling during some moment of time, but no such moment can be identified. Every instant reveals only location, never movement. This paradox differs fundamentally from its predecessors. The dichotomy and Achilles both accept that motion occurs over intervals of time, then argue about whether infinite subdivisions make such motion impossible. The arrow paradox questions whether motion makes sense even within intervals. Before you can worry about infinite division, you must explain what motion means at any scale of time whatsoever. Zeno has shifted the battlefield from the mathematics of infinity to the metaphysics of change. The ancient world found this paradox deeply unsettling, precisely because it seemed to undermine something more basic than our ability to complete journeys. It challenged whether motion was even coherent as a concept. Aristotle, who devoted considerable effort to refuting Zeno, recognized the arrow as perhaps the most dangerous of the paradoxes. His response invoked the distinction between actuality and potentiality. The arrow is actually at its current location, but potentially at other locations, and this potentiality constitutes motion. The arrow at any instant is actually here and potentially there, and the transition from potentiality to actuality is what moving means. But does this truly answer Zeno? Potentiality describes what might happen next, not what is happening now. To say the arrow is potentially elsewhere tells us about the future, not about the present instant. The question remains, within this instant, with no duration and no futurity contained in it, what makes the arrow a moving arrow rather than a stationary arrow that happens to be somewhere else a moment later? The paradox exposes a profound puzzle about the relationship between instants and intervals. We think of time as composed of instants the way a line is composed of points, but points have no length, and instants have no duration. A line made entirely of lengthless points should have no length. Time made entirely of durationless instants should have no duration. Yet lines have length and time has duration. Something in this picture fails to cohere. The same puzzle appears in motion itself. Motion is change of position over time, but change requires difference, and difference requires comparison between two states. An instant contains only one state. There is no before or after within it, no earlier or later, no change whatsoever. The instant is frozen by definition. Then how do instantaneous states, each frozen and changeless, combine to create the flowing continuity of motion that we observe? You might suggest that motion at an instant could be defined by the arrow's velocity at that instant. Calculus would later provide such a definition, velocity as the instantaneous rate of change of position. But this moves the mystery rather than solving it. What does rate of change mean at an instant? A rate measures how much something changes per unit of time. At an instant with no duration, no time passes. How can anything change per unit of time when there is no time? Calculus defines instantaneous velocity as a limit, the velocity the arrow approaches, as we consider smaller and smaller time intervals around the instant in question. This works mathematically. It allows precise predictions about where the arrow will be, but it defines motion at an instant by reference to intervals around that instant, not by anything happening within the instant itself. The instant remains frozen. Velocity at an instant becomes a mathematical abstraction describing the relationship between positions at different instants, not a physical reality existing at the instant. Perhaps this reveals something essential about motion. Perhaps motion is not a property of individual instants, but a property of sequences of instants. The arrow is not moving at any instant. Rather, the sequence of instants displays a pattern, and we call that pattern motion. Motion becomes a relationship, not a thing. It exists between moments, not within them. But this interpretation, while mathematically serviceable, leaves the arrow paradox philosophically undefeated. Zeno claimed motion was incoherent. If motion turns out to be not a real property, but a relational pattern we impose on sequences of static states, has Zeno not won? If nothing is actually moving at any moment, if motion is merely a description of how positions differ across time, then in what sense does motion exist? The paradox grows sharper when you consider that we have direct experience of motion. You do not experience a sequence of static positions and infer motion. You experience motion itself, continuous and flowing. The arrow does not appear to you as a series of frozen images. Its flight looks smooth and seamless. Yet when you try to locate this motion within time, to identify what the arrow is doing at any particular instant, the motion vanishes. Experience presents motion as fundamental. Analysis reveals only position. Something in our conceptual apparatus cannot capture what our senses report. Modern physics has not eliminated this tension. Quantum mechanics suggests that position and velocity cannot both be precisely determined simultaneously, which adds another layer of mystery but does not resolve the conceptual problem. If the arrow cannot have both a definite position and a definite velocity at the same instant, does that make motion more comprehensible or less? Relativity theory reveals that simultaneity depends on the observer's reference frame, but an arrow moving in one frame is still described by a sequence of positions, each existing at an instant. The arrow paradox continues to hover over every attempt to understand change and becoming. It suggests that time itself might not work the way we imagine. If instants are real, and time is made of instants, then motion seems impossible. If motion is real, then perhaps instants are not the fundamental constituents of time. Perhaps time is not made of points at all, but is genuinely continuous in a way that resists decomposition into moments. Yet this opens new mysteries. What is a continuum that cannot be analyzed into parts? How can time be genuinely indivisible when we clearly can consider earlier and later within it? These questions would echo through philosophy for millennia. Every thinker who considered the nature of time, from Augustine's Meditations on the Specious Present to Henry Bergson's distinction between clock time and experience duration, wrestled with the ghosts Zeno raised. The arrow paradox planted a seed of doubt about whether the mathematical tools we use to describe reality actually capture what reality is. Mathematics requires us to treat time as composed of instants, but this treatment may be convenient fiction rather than fundamental truth. The arrow paradox exposes a wound in our concept of time itself, but Zeno had one more weapon, stranger than the others, involving relative motion and the nature of simultaneity. Among Zeno's arsenal of arguments, one stands apart for its sheer obscurity. Ancient commentators struggled to understand it. Modern scholars debate what it even claimed. The paradox known as the stadium arrives through history wrapped in confusion, its original formulation lost, its purpose unclear. Yet this strangest of Zeno's weapons may reveal something essential about why he constructed paradoxes at all. The stadium paradox involves three rows of objects arranged in parallel lines. Imagine three sets of bodies, each set containing an equal number of identical units. One row remains stationary, the other two rows move in opposite directions, passing both the fixed row and each other. Aristotle, our primary source for this paradox, found Zeno's conclusion baffling that half a given time equals double that time. The argument appears to hinge on relative motion and what counts as a unit of time. As the moving rows pass each other, each object in one row passes twice as many objects in the opposing row as it passes in the stationary row during the same interval. If passing one object defines 1 unit of time, then passing two objects should define 2 units. Yet the same duration has somehow produced both 1 unit and 2 units of time. Half equals double. The absurdity speaks for itself. Or does it? Aristotle dismissed this reasoning as fallacious, noting that Zeno confused time measured against stationary objects with time measured against moving objects. The error seemed obvious. An object moving past another moving object covers more ground than when moving past a stationary object. But this tells us nothing paradoxical about time itself. Ancient readers largely agreed. The stadium paradox became a footnote, an argument so flawed it hardly deserved the name paradox. Yet perhaps we have misunderstood what Zeno intended. The stadium may not have been about time at all, but about the impossibility of discrete units combining to form continuous motion. If objects truly moved in jumps from one position to the next, relative motion would produce precisely the kind of absurdity Zeno described. The paradox might have targeted those who tried to escape his other arguments by proposing that space and time came in indivisible chunks. Look, Zeno might have said, if you insist on atoms of space or moments of time, you create contradictions worse than the ones you hope to avoid. This interpretation remains speculative. The stadium paradox endures as a puzzle wrapped in a mystery, an argument whose very obscurity tells us something about the fragility of philosophical transmission. Words carved in stone can last millennia. Ideas written on papyrus scrolls depend on continuous copying, each generation preserving what the previous generation valued. When later philosophers found an argument incomprehensible, they often copied it incompletely or not at all. The stadium survived not because it was understood, but because Aristotle mentioned it. We possess the fossil of an argument, not the living thought. But Zeno's paradoxes of motion formed only half his assault on common sense. He aimed his other weapons at plurality itself, at the simple claim that many things exist. If things exist as separate entities, Zeno argued, then each thing must have some size. Otherwise it would be nothing. But if something has size, it has parts, one part here and another part there. And if it has parts, those parts are themselves things, each requiring its own size, each divisible into further parts. You can never reach a final component because anything genuinely indivisible would have no size, would be nothing at all. Yet adding together infinite nothings yields nothing. Therefore, if things exist, they must be infinitely large, built from infinite parts each having size. The trap closes from the other direction as well. Take any object and begin dividing it. Cut it in half, then cut the halves in half, and continue. Two possibilities present themselves. Either you eventually reach something genuinely indivisible, or you can continue dividing forever. If you reach indivisible units, these units have no size. For anything with size can be conceptually divided into left and right portions, but things built from sizeless units have no size themselves. If you can divide forever, however, you never finish the process of determining what the object actually contains. It remains forever mysterious, forever dissolving under analysis. Here Zeno revealed his deepest strategy. Every attempt to say how many things exist leads to contradiction. Claim there are atoms, indivisible units, and you must explain how sizeless points combine to create sized objects. Claim there is infinite divisibility, and you must explain how any object has determinate properties when analysis never terminates. Insist things are separate, and you face the question of what exists between them. Say they touch, and they merge into one. Say they do not touch, and something must occupy the gap, creating more things requiring more explanations. The paradoxes of plurality function differently from the paradoxes of motion. When Zeno argues against motion, experience rebels. We see arrows fly regardless of logic. But when Zeno argues against plurality, intuition provides less guidance. How many things exist feels more like a conceptual question than an empirical one. Perhaps reality genuinely is one undivided whole, and our perception of separate objects represents a kind of cognitive error, a failure to grasp the unified nature of what is. This conclusion would have pleased Parmenides enormously. The old philosopher had declared that only one thing exists, eternal and unchanging. Critics scoffed. Look around, they said. We see many things, constantly changing. Parmenides must be mad, or speaking in riddles. Then his student Zeno stepped forward with a simple challenge. You claim many things exist and move? Very well. Explain how without contradiction. The critics tried. Their explanations collapsed into absurdity. Perhaps Parmenides was not mad after all. Understanding Zeno's paradoxes of plurality requires recognizing what he meant by a thing. He did not mean merely a physical object, a stone or a tree. He meant any supposedly distinct entity, any item you might count as separate from other items. Numbers themselves qualify. So do properties, relations, and abstract concepts. If you say there are two things, or three, or any number other than one, Zeno demands you explain what makes them two rather than infinitely many or indivisibly one. The question strikes at the foundation of counting itself. When you say there are 5 apples in a basket, you treat each apple as a unit, but each apple has parts: skin, flesh, seeds, stem. Are those parts also things? They have parts too, molecules and atoms, which have parts of their own. At what level does thingness begin? Or perhaps the basket and its entire contents form one thing, temporarily configured in a particular way, but not genuinely divided into separate entities. These arguments possess a dizzying quality. They seem to prove too much. If nothing can be many, then Zeno's arguments themselves are not many arguments, but one argument, or perhaps not even one argument, but no arguments at all, since one implies possible contrast with two. The paradoxes threaten to devour themselves, to undermine the very language needed to express them. Yet that self-consuming quality may have been precisely what Zeno intended. He was not building a positive theory, He was demolishing the theories of others by showing that common assumptions about reality lead to incoherence. Think things are many? Here is why that makes no sense. Think things move? Here is why that makes no sense either. The proper response, Zeno suggested, was not to refine these claims, but to abandon them. Trust Parmenides. Reality is one, all else is illusion. For centuries, these paradoxes were treated as clever sophistry, troublesome but not truly threatening. Then philosophers realized they could not actually solve them. Aristotle confronted Zeno's paradoxes roughly a century after their creation, and his frustration bleeds through the pages of his Physics. He understood what was at stake. These were not mere logical games, but challenges to the entire foundation of natural philosophy. If motion was impossible, if plurality was incoherent, then the entire project of understanding the physical world collapsed before it could begin. So Aristotle crafted his response with care, drawing a distinction that seemed to cut through Zeno's arguments like sunlight through morning fog. The key, Aristotle argued, lay in recognizing two different ways something could be infinite. There was potential infinity and actual infinity, and confusing them was where Zeno had led his audience astray. A line could be potentially divisible into infinitely many parts, but this did not mean it actually consisted of infinitely many parts already present, waiting to be counted. When you walked across a room, you did not have to complete an actual infinity of tasks. You simply moved through a continuous space that could be divided if you chose to, but was not already divided. The distinction felt right. It matched intuition and observation. It preserved the reality of motion while acknowledging the logical force of Zeno's arguments. For nearly 2,000 years, philosophers treated Aristotle's response as essentially correct. Even if the details remained fuzzy, the paradoxes had been answered, or at least contained. They became historical curiosities, examples of clever sophistry overcome by sound thinking. But the nagging problem never quite disappeared. Aristotle had shifted the terms of debate, not resolved the underlying difficulty. Zeno's paradoxes were constructed as reductio arguments. If you accept that space is infinitely divisible, then certain absurdities follow. Aristotle's response essentially said, space is infinitely divisible, but only potentially, not actually. This avoided calling the infinite series actual, but it did not explain how motion traversed what remained in principle an infinite divisibility. The runner still had to cover half the distance, then half the remaining distance, then half of that. Whether you called these divisions potential or actual, the logical structure remained infinitely many intervals, each of which required time to cross. Aristotle himself seemed to sense this weakness. He offered multiple responses to different formulations of the paradoxes, sometimes emphasizing the continuity of motion, sometimes focusing on the nature of time, sometimes invoking the potential-actual distinction. The multiplication of answers suggested that no single response fully satisfied even its author. Medieval philosophers inherited both Zeno's paradoxes and Aristotle's responses, and they added their own complications. Islamic and Christian thinkers debated the nature of matter, time, and divine power with a precision that rivaled or exceeded the ancient Greeks. They asked whether space and time were themselves substances, or merely relations between things. They wondered whether God could create actual infinities, or whether such entities were logical contradictions even divine omnipotence could not overcome. The atomists among medieval scholars saw in Zeno's paradoxes a possible argument for indivisible units. If dividing matter infinitely led to contradictions, perhaps matter was composed of fundamental particles that could not be subdivided. Physical atoms would eliminate infinite divisibility, and thereby dissolve Zeno's arguments. But this solution created its own puzzles. If atoms were extended in space, why could they not be divided? If they were not extended, how could any collection of them produce extended objects? The paradoxes simply migrated from one level to another. Other medieval thinkers explored the mathematical structure of Zeno's challenges more carefully. Nicole Oresme, a 14th century French philosopher, investigated infinite series and developed graphical methods for representing changing quantities. He understood that an infinite series could, in principle, sum to a finite value, but he lacked the mathematical framework to prove this rigorously or to explain precisely what such summation meant. His insights remained suggestive rather than conclusive. The fundamental problem was this: to resolve Zeno's paradoxes mathematically required making precise sense of infinite processes. You needed to explain what it meant for infinitely many terms to sum to a finite number. You needed a rigorous concept of a limit, a way of talking about approaching a value without necessarily reaching it, and a clear distinction between a process and its endpoint. Ancient and medieval mathematics possessed none of these tools. Greek geometry was magnificent in its rigor, but it dealt with finite constructions and avoided the infinite wherever possible. Euclidean proofs never invoked completed infinite processes. Medieval algebra and arithmetic expanded computational power, but similarly sidestepped the conceptual difficulties Zeno had exposed. Mathematicians could calculate approximations, could see that doubling the number of terms in certain series brought them closer to specific values, but they could not explain what was happening in the infinite limit. The scientific revolution of the 16th and 17th centuries brought renewed attention to Zeno. Galileo Galilei grappled with paradoxes of infinity in his dialogues concerning two new sciences, discovering that infinite sets had strange properties. You could pair every positive integer with every even positive integer, suggesting that these two infinite collections were somehow the same size, even though one seemed twice as large as the other. This was delightful and disturbing, and it showed that infinity did not behave like finite quantities, but it did not resolve Zeno's challenge. Johannes Kepler and Bonaventura Cavalieri developed early methods of integration, treating areas and volumes as composed of infinitely many infinitesimally thin slices. These methods worked spectacularly well for practical calculations, but their logical foundations remained obscure. What exactly was an infinitesimal? Was it a number greater than zero? Or was it zero itself? If greater than zero, then infinitely many of them should sum to infinity. If actually zero, then infinitely many of them should sum to zero. Either way seemed problematic, yet the calculations consistently produced correct results. Natural philosophers could now compute trajectories, analyze motion, and predict planetary positions with unprecedented accuracy. But Zeno's question remained unanswered. How does motion actually occur? How does something traverse an infinitely divisible space? The practical success of mathematical physics made the question seem less urgent, but urgency and resolution are different things. A method that works is not the same as an explanation of why it works. By the middle of the 17th century, the stage was set for a genuine breakthrough. The problems were clear: motion, continuity, infinite series, and the relationship between finite quantities and infinite processes. The practical needs were pressing. Physics required better mathematical tools, and several brilliant minds were converging on similar insights, each approaching from different directions. The breakthrough came not from philosophy but from a new branch of mathematics that could for the first time make rigorous sense of infinity. The mathematicians of the 17th century faced a practical crisis. Navigation demanded accurate tables of planetary motion. Artillery officers needed to predict the arc of cannonballs. Engineers building fountains for royal gardens required calculations about flowing water and pressure. Every advance in mechanical understanding ran headlong into problems involving curves, rates of change, and accumulating quantities. The old geometry of Euclid, brilliant as it was, could not handle motion. It described static shapes with perfect precision but fell silent when asked about trajectories, velocities, or areas bounded by curved lines. Worse still, these practical problems inevitably involved something ancient mathematics had learned to fear: the infinite. Isaac Newton approached infinity through physics. Born in 1642, the same year Galileo died, Newton inherited a universe in mathematical crisis. Galileo had shown that falling objects accelerate continuously, their speed increasing smoothly from instant to instant. But how could anyone calculate the distance traveled when velocity itself was changing? The problem required adding up infinitely many, infinitely small contributions, a task that seemed to mock human reason just as thoroughly as Zeno's paradoxes had mocked human motion. Newton, working in isolation during plague years at his family estate in Woolsthorpe, developed a method he called fluxions. He imagined quantities flowing through time, growing or shrinking continuously, and devised rules for calculating their rates of change and their accumulated totals. Gottfried Wilhelm Leibniz, working independently in Germany, arrived at similar conclusions through different reasoning. Where Newton thought in terms of physical motion and flowing quantities, Leibniz approached the problem through pure mathematics, seeking general principles that would apply to any smooth curve. He developed an elegant notation, introducing symbols that students still use today: the elongated S for integration, the notation di over dx for derivatives. More importantly, both men grasped the fundamental insight that would transform mathematics. They recognized that two seemingly different operations, finding instantaneous rates of change and calculating accumulated totals, were inverse processes, two sides of the same conceptual coin. Their key innovation was the limit. This concept, still challenging for students encountering it today, provided a way to speak rigorously about approaching a value without claiming to reach it. Consider a ball rolling down a ramp, picking up speed as it descends. At any particular instant, it has some velocity. But what does velocity at an instant mean? The ball covers no distance in zero time, giving the meaningless ratio of 0 over 0. The calculus answer: examine what happens as the time interval gets smaller and smaller. Calculate the distance covered in 1 second, then in half a second, then a quarter second, continuing indefinitely. These ratios approach a particular value. That limiting value is the instantaneous velocity, not because the ball somehow moves during a durationless instant, but because the ratio gets arbitrarily close to that number as the time interval shrinks. This notion of a limit allowed mathematicians to compute with the infinite while keeping it, in some sense, at arm's length. They never completed infinitely many steps. Instead, they described what would happen if such completion were possible, defining answers as the values that finite processes approached ever more closely. The method worked spectacularly well. Newton used his calculus to derive Kepler's laws of planetary motion from basic principles of gravitation. Engineers calculated the curves of hanging chains and the paths of projectiles. The mathematics of flowing quantities, of continuous change, of smooth curves and accumulating totals became the language of nature itself. The infinite series fell to the same approach. Take the puzzle of Achilles and the tortoise. Achilles must cover half the remaining distance, then half of what remains after that, then half again indefinitely. Suppose the total distance equals 1 unit. Achilles runs 1/2, then 1/4, then 1/8, then 1/16, continuing without end. How far has he gone when all these pieces are added? Before calculus, this question produced only confusion. Afterward, mathematicians could prove rigorously that the sum approaches exactly 1, not approximately 1, not arbitrarily close to 1, but precisely 1. The proof depends on understanding that an infinite sum can have a finite limit, that approaching closer and closer without end is different from never arriving. The technique generalizes. Write out the partial sums: 1/2 equals 0.5, 1/2 plus 1/4 equals 0.75. Add 1/8 to reach 0.875. Continue adding terms, and the sum creeps ever closer to 1, never exceeding it, never stopping its approach, but drawing so near that the difference becomes unmeasurably small. Calculus formalized this intuition into a rigorous argument. For any distance from 1, no matter how tiny, eventually the sum gets closer than that. The infinite process converges. The journey ends. Does this solve Zeno? It certainly dissolves the practical difficulty. If someone asks how far Achilles travels by completing infinitely many stages, mathematics now offers a precise answer: exactly the full distance. The divergence between logic and experience vanishes. The mathematical account of motion aligns with observation. Calculus proves that infinite processes can yield finite outcomes, that unending division does not necessarily produce unending magnitude. The dichotomy and Achilles paradoxes, understood as mathematical challenges, admit mathematical resolution. But Zeno was not merely posing mathematical problems. His target was the coherence of motion itself, the conceptual possibility of traversing divided space. Calculus shows how to calculate with infinite sequences, not whether actually completing them makes sense. The limit describes what value a sequence approaches, not whether a physical runner genuinely performs infinitely many distinct tasks. Mathematics can assign a sum to the series without explaining how Achilles accomplishes the summation. The gap between calculation and completion remains. Consider the arrow paradox, which calculus addresses differently. Newton's fluxions and Leibniz's differentials provided a way to describe instantaneous velocity mathematically. The velocity at a moment is defined as the limit of average velocities over shrinking time intervals. This defines the concept without requiring that motion somehow occur within a durationless instant. The arrow has a velocity at each moment because there exists a number that the relevant ratios approach as intervals shrink. Whether this constitutes motion at an instant or merely a useful mathematical representation of motion near an instant remains philosophically open. The deeper question persists: has mathematics answered Zeno, or merely learned to work around him? Calculus provides tools of tremendous power and precision. It allows physicists to predict trajectories, engineers to design machines, astronomers to calculate orbits. Every triumph of modern science depends on mathematics that handles infinity routinely, almost casually. Yet the conceptual puzzles that motivated Zeno's arguments remain incompletely resolved. Mathematics shows that infinite division need not prevent motion from occurring in finite time. It does not explain what it means for physical space to be infinitely divisible, or whether spatial points truly exist, or how motion at an instant differs from rest. Some mathematicians recognized this distinction. They celebrated calculus as a magnificent practical tool, while acknowledging that its foundations remained philosophically murky. Newton himself used geometric arguments in his published work, presenting results proven through his calculus methods, but expressed in classical geometric form, perhaps sensing that his contemporaries would find the limit concept insufficiently rigorous. Leibniz defended his methods vigorously, but acknowledged that infinitesimals, the vanishingly small quantities he manipulated, occupied an ambiguous status between something and nothing. The techniques worked. The justifications felt incomplete. For a century and a half, mathematicians used calculus without fully understanding why it worked. They obtained correct answers through methods that seemed logically suspect, trading philosophical purity for practical power. Only in the 1800s did a new generation undertake the task of placing calculus on completely rigorous foundations, defining limits with airtight precision, banishing infinitesimals that were somehow non-zero yet smaller than any actual number. This formalization resolved the mathematical uncertainties, proving that calculus rested on solid logical ground. But even then, the philosophical questions Zeno raised about the nature of space, time, and motion remained untouched. Mathematics had learned to compute with confidence. It had not explained what ultimately was being computed. Calculus offered mathematical closure, but in the 19th century, a new generation of mathematicians realized that infinity itself was stranger and more varied than anyone had imagined. Calculus had given mathematicians the power to work with infinity, to sum infinite series and find slopes of curves at single points. By the middle of the 19th century, the techniques felt secure, the results reliable. Engineers built bridges using equations that involved limits and infinitesimals. Physicists described motion with derivatives and integrals. The practical problems were solved. Yet a German mathematician working in relative obscurity was about to prove that infinity itself was far stranger than anyone had imagined, and in doing so, he would reopen every question Zeno had ever posed. Georg Cantor was born in St. Petersburg in 1845, the son of a merchant who moved the family to Germany when Georg was 11. He studied mathematics at the University of Berlin, where he fell under the influence of Karl Weierstrass, one of the architects of rigorous analysis. Cantor earned his doctorate in 1867 and took a position at the University of Halle, a respectable but not prestigious institution. There, far from the mathematical centers of Berlin and Göttingen, he began investigating the nature of infinite sets. The work started innocuously enough. Cantor was studying trigonometric series, trying to understand when such series represent functions uniquely. The investigation led him to questions about collections of points on a line. How many points are there in a line segment? Infinitely many, obviously. But what does that mean? Cantor began to wonder whether all infinite collections were the same size. The question sounds almost naive. Infinity is infinity, boundless and unlimited. What could it mean for one infinity to be larger than another? Yet Cantor discovered that it meant something quite precise, and the implications were staggering. He began with the simplest infinite set, the natural numbers, 1, 2, 3, 4, and so on without end. This was the infinity everyone understood intuitively, the infinity of counting forever. Cantor called this infinity countable. A set is countable if you can pair each element with a natural number, even if the pairing goes on forever. Now consider the rational numbers, the fractions. Every fraction can be expressed as one integer divided by another. At first glance, there seem to be vastly more fractions than natural numbers. Between any two natural numbers lie infinitely many fractions. Between 1 and 2, you find 1 and 1/2, 1 and 1/3, 1 and 1/4, and endlessly onward. Surely this infinity must be larger. Cantor proved otherwise. In 1874, he demonstrated that the rational numbers are countable. You can list them in a sequence, pairing each fraction with a natural number. The method is ingenious. Arrange all fractions in a grid, with numerators increasing along one axis and denominators along the other. Then trace a path through this grid that visits every fraction exactly once. The path zigzags systematically, ensuring that no fraction is missed. This means the infinity of fractions is the same size as the infinity of natural numbers. Both sets have the same cardinality, to use Cantor's term. This result was surprising but not shocking. The next result was both. Cantor turned his attention to the real numbers, which include not just integers and fractions, but also irrational numbers like the square root of 2 and pi. These numbers fill the number line completely, with no gaps. Between any two real numbers, no matter how close, lie infinitely many more real numbers. Do the real numbers form a countable infinity, like the natural numbers and rationals? In 1874, Cantor proved they do not. His proof was indirect, a reductio ad absurdum that Zeno would have appreciated. Assume for the sake of argument that the real numbers are countable. That means you could list them in a sequence: first real number, second real number, third real number, and so on. Cantor showed this leads to a contradiction. No matter how you try to list the real numbers, you can always construct a real number not on your list. Therefore, the real numbers cannot be listed. They form an uncountable infinity, fundamentally larger than the infinity of natural numbers. The proof method, now called Cantor's diagonal argument, became one of the most famous techniques in mathematics. To see why no list can contain all real numbers between 0 and 1, imagine writing them in decimal form. The first number might be 0.14159, and so on. The second might be 0.3333, continuing forever. The third might be 0.71828 and onward. Now construct a new number by looking at the diagonal. Take the first digit of the first number, the second digit of the second number, the third digit of the third number, and so on. Change each digit you find. If the diagonal digit is 5, make yours 6. If it is 3, make yours 4. The number you construct differs from every number on the list in at least one decimal place. Therefore, it is not on the list, contradicting the assumption that the list was complete. Cantor had shattered the naive notion that infinity is infinity. There are at least two distinct sizes of infinity, and he would go on to prove there are infinitely many sizes, an endless hierarchy of infinities, each transcending the one before. The mathematical community reacted with a mixture of awe and horror. Leopold Kronecker, one of the most influential mathematicians in Germany, rejected Cantor's work entirely. Kronecker believed that only the natural numbers were truly real, that all mathematics should be constructible from finite operations. He allegedly called Cantor a corrupter of youth and worked to block his career advancement. The attacks devastated Cantor, who suffered recurring bouts of depression throughout his later life. Yet others recognized the profound importance of what Cantor had discovered. David Hilbert, who would become the leading mathematician of the early 20th century, declared that no one shall expel us from the paradise that Cantor has created. Set theory, built on Cantor's foundations, became the basis for all of modern mathematics. For Zeno's paradoxes, the implications were unsettling. Calculus had seemed to tame infinity by showing that infinite series could have finite sums, but now infinity itself had splintered into multiple, incomparable sizes. When Zeno argued that a line segment contains infinitely many points, which infinity did he mean? The points could be labelled with natural numbers if you picked them out one by one in some systematic way, but the full continuum of points between any two locations is uncountable, a larger infinity altogether. This distinction complicated every attempt to dismiss Zeno's arguments. Saying that motion covers infinitely many points no longer specified what kind of infinite collection was involved. The difference between countable and uncountable infinities suggested that infinite divisibility was not a simple concept, but a tangled hierarchy of increasingly abstract infinities. Moreover, Cantor's work revealed that infinity was not merely a practical tool for calculation, but a mathematical object demanding rigorous definition. This raised a question calculus had sidestepped. What is the relationship between the mathematical continuum and physical space? Is space actually composed of uncountably many points, or is that merely a useful model? Zeno had asked whether space is infinitely divisible. Cantor proved that mathematical continua are uncountably infinite. Whether physical space shares that property remained an open question. Enter Bertrand Russell. Born in 1872, Russell became one of the most prominent philosophers of the 20th century, contributing to logic, epistemology, social philosophy, and the popular understanding of philosophy itself. In his early career, he focused intensely on the foundations of mathematics. Russell had been trained in the idealist tradition that dominated British philosophy in the late 19th century, but he broke dramatically from idealism after encountering the work of Giuseppe Peano and Gottlob Frege, who were attempting to reduce all mathematics to logic. Russell became convinced that philosophy had been insufficiently rigorous, that it needed the precision of mathematical logic to make progress on ancient problems. When Russell turned his attention to Zeno around 1900, he saw something previous generations had missed. The paradoxes were not merely logical tricks or failures of ancient mathematics. They were, Russell argued, genuine problems for any theory of space, time, and motion. Calculus had provided methods for calculation, but it had not addressed the conceptual questions at the heart of Zeno's arguments. Russell pointed out that calculus assumes the real number continuum, which has the structure Cantor had analyzed. This continuum is dense, meaning between any 2 points you can always find another point, and complete, meaning there are no gaps. But does time have this structure? Does space? These are empirical questions about the physical world, not mathematical theorems. Furthermore, the arrow paradox remained troubling. At any instant, an object occupies a precise location. Its velocity is defined as a limit, a derivative, a mathematical abstraction. But what does it mean physically to have a velocity at an instant? If an instant has no duration, how can motion occur within it? Calculus tells us how to calculate instantaneous velocity, but it does not explain what it means for motion to exist at a durationless moment. Russell's writings on Zeno, particularly in his 1914 book, Our Knowledge of the External World, brought the paradoxes back into mainstream philosophical discussion. He argued that modern logic and set theory had given philosophy new tools to address ancient questions, but that the questions remained difficult and unresolved. Where previous centuries had treated Zeno as an interesting historical curiosity, Russell insisted that the paradoxes were live problems requiring serious engagement. The recognition spread. Other philosophers and mathematicians began reconsidering Zeno in light of modern developments. Some argued that Cantor's hierarchy of infinities made the paradoxes worse, not better. Others suggested that the paradoxes revealed fundamental limitations in our concepts of space and time. Still others maintained that careful analysis dissolved the paradoxes, but disagreed sharply about what that analysis should conclude. What became clear was that calculus had solved certain technical problems without resolving the underlying philosophical mysteries. You could calculate how long Achilles takes to overtake the tortoise, but explaining what it means to complete infinitely many tasks remained elusive. You could describe motion mathematically using continuous functions, but articulating what motion is at a single instant resisted clear formulation. Cantor had shown that infinity is not one thing but many. Russell had shown that Zeno's paradoxes still bite, even after centuries of mathematical progress. The ancient puzzles refused to die because they touched something deeper than calculation, something about the relationship between mathematical models and physical reality, between abstract structure and lived experience. Just as mathematics seemed to have contained Zeno, physics began revealing that space and time might be even stranger than the ancient Greeks imagined. The 20th century arrived with mathematics apparently victorious over Zeno. Calculus had tamed infinite series, set theory had mapped the landscape of infinity itself, and analysis had placed limits on rigorous foundations. Philosophy textbooks began treating the ancient paradoxes as historical curiosities, problems that medieval thinkers struggled with before the development of proper mathematical tools. Then physics looked more carefully at space and time themselves, and Zeno's ghost stirred once more. Albert Einstein published his special theory of relativity in 1905, a year often called his annus mirabilis. Among several revolutionary papers, this one dismantled assumptions about time and space that seemed obvious to everyone from Zeno to Newton. Time, Einstein showed, was not absolute. Two events that appeared simultaneous to one observer might occur at different moments for another observer moving at a different velocity. Space and time were not separate containers within which events unfolded, but rather aspects of a single geometric structure, space-time. The interval between events depended on the observer's motion. This revelation struck at the heart of several of Zeno's paradoxes. The arrow paradox had asked what it meant for an object to be in motion at a single instant of time. But if time itself varied depending on the observer's reference frame, the very notion of a universal instant became questionable. An arrow in flight existed not at a series of frozen moments but along a world line through space-time, a four-dimensional path that mingled space and time inextricably. Motion was not something that happened in time. It was the geometric shape of an object's trajectory through space-time itself. Yet this elegant reformulation did not eliminate the conceptual problem. You could still divide the arrow's world line into infinitely many points. You could still ask what it meant for the arrow to be moving at any single point along that world line. Einstein had shown that space and time were more deeply connected than anyone imagined, that they formed a unified continuum, but a continuum could still be divided infinitely. The paradox transformed but did not dissolve. General Relativity, published in 1915, revealed that this space-time could curve, that matter and energy warped its geometry, that gravity was not a force but the shape of space-time itself. This was philosophically stunning and mathematically beautiful. It also left Zeno's questions intact. Curved or flat, space-time remained a continuum. The mathematics of general relativity relied on smooth, infinitely divisible manifolds. Every solution to Einstein's field equations assumed that you could take derivatives at every point, that space and time had structure at arbitrarily small scales. Physics had refined the stage on which motion occurred. It had not explained how motion was possible. Then came quantum mechanics, and with it a different kind of strangeness. In 1927, Werner Heisenberg formulated his uncertainty principle, showing that certain pairs of properties could not both be measured with arbitrary precision. The most famous pairing was position and momentum. The more precisely you determined where a particle was located, the less precisely you could know its momentum. The more precisely you knew its momentum, the less precisely you could determine its position. This was not a limitation of measurement technology. It was a fundamental feature of reality. A particle did not have both a definite position and a definite momentum simultaneously. At the quantum scale, the classical picture of a particle with a definite location moving along a definite path simply did not apply. Instead, quantum mechanics described particles through wave functions, mathematical objects, that gave probabilities for finding a particle in various locations or with various momenta. Here was a direct challenge to the arrow paradox. Zeno had assumed that at each instant an arrow occupied a precise position and had a definite state of motion. But quantum mechanics suggested that this assumption broke down for fundamental particles. An electron could not be said to occupy a precise location while simultaneously possessing a definite velocity. The very question Zeno posed might rest on false premises about the nature of physical objects. Does this solve the paradox? Only if you believe that the behavior of electrons dictates the behavior of arrows. The arrow in Zeno's paradox was a macroscopic object, and macroscopic objects emerge from quantum mechanics through a process called decoherence, in which quantum superpositions collapse into apparently classical behavior. At human scales, quantum uncertainty becomes negligible. The arrow does appear to have both a position and a velocity at each moment. So Zeno's question returns: what does it mean for this classical arrow to be moving at a single instant? The quantum realm offered a different kind of challenge to infinite divisibility. In 1900, Max Planck had introduced a fundamental constant to explain blackbody radiation, a constant that now bears his name. This Planck constant suggested that energy came in discrete packets, quanta, rather than continuous flows. Light was not a smooth wave, but a collection of photons. Atoms could not have arbitrary energies, but only specific quantized energy levels. In the 1950s, physicists began exploring what this quantization might mean for space and time themselves. They found natural units of length, time, and mass constructed from fundamental constants: the speed of light, the gravitational constant, and the Planck constant. The Planck length worked out to approximately 1.6 times 10 to the negative 35 meters. This was not merely small, it was incomprehensibly tiny, roughly 10 to the negative 20 times the diameter of a proton. Below the Planck length, quantum fluctuations in spacetime itself became so violent that the smooth continuum assumed by general relativity broke down. Physicists could not calculate what happened at scales smaller than this, because the very notion of distance and duration dissolved into quantum foam. Some theorists proposed that spacetime might be fundamentally discrete, composed of minimum units that could not be divided further. If spacetime were truly quantized, Zeno's infinite division would have a stopping point. You could not divide the distance between the arrow and its target infinitely, because eventually you would reach a fundamental unit of length that had no internal structure. The dichotomy would terminate not in mathematical convergence, but in physical discreteness. This sounds like resolution, but notice what it requires: abandoning the assumption that space is infinitely divisible. Zeno would approve. His paradoxes were reductio arguments, demonstrations that common assumptions led to absurdity. If you grant that space is continuous and infinitely divisible, he argued, motion becomes impossible. The modern response would be perhaps space is not continuous. Perhaps at the deepest level, reality is digital rather than analog, composed of discrete units rather than smooth continuity. Yet this solution spawns new paradoxes. If spacetime is quantized, what happens between the units? If an electron moves from one unit of space to an adjacent unit, does it pass through intermediate locations, or does it teleport discontinuously? If motion is discontinuous, does it make sense to speak of velocity, which is defined as the continuous rate of change of position? The classical problem of motion at an instant transforms into the quantum problem of motion between discrete states. Furthermore, the evidence for quantized spacetime remains indirect and disputed. No experiment has directly measured the structure of spacetime at the Planck scale. Some approaches to quantum gravity, such as loop quantum gravity, predict discrete spacetime. Others, such as string theory, retain smooth spacetime even at very small scales but embed it in higher dimensions. The question remains open. Even if spacetime is quantized, the relationship between physical reality and mathematical description remains puzzling. The mathematics we use to predict quantum behavior relies on continuous functions, complex numbers, infinite-dimensional Hilbert spaces. We calculate using calculus and smooth manifolds, then interpret the results as describing a fundamentally discrete reality. The map is continuous, but the territory might not be. How do we reconcile this? Relativity and quantum mechanics have transformed our understanding of space, time, and matter. They have revealed that the universe operates by rules far stranger than Zeno or his contemporaries imagined. But in transforming the paradoxes, physics has not eliminated them. Instead, it has relocated them to deeper levels of description. The ancient questions about continuity, infinity, and the nature of change persist in new forms, now entangled with questions about observation, measurement, and the relationship between quantum and classical worlds. After 25 centuries, Zeno's paradoxes remain unresolved in a fundamental sense, but perhaps their persistence teaches us something valuable. In the spring of 1902, Bertrand Russell delivered a paper to the London Mathematical Society that did something curious. Rather than celebrate the triumph of modern mathematics over ancient confusion, he suggested that Zeno of Elea had posed questions that remained, in an important sense, unanswered. The room contained some of the finest mathematical minds in Britain, men who worked daily with infinite series and limits, who could prove with rigor that Achilles overtakes the tortoise, and that arrows do indeed move. Yet Russell insisted that solving a paradox mathematically and dissolving it philosophically were not the same thing. The distinction he drew that afternoon cuts to the heart of why these ancient puzzles refused to die. Mathematics can show how infinite processes converge. Calculus provides tools to sum infinite series and obtain finite results. Set theory maps the strange landscape of different infinities. Physics describes motion with extraordinary precision, but none of these achievements quite answer the question Zeno posed. He did not ask whether motion occurs, he asked how it is possible. He did not wonder whether Achilles catches the tortoise. He wondered how completing infinitely many tasks can happen in finite time. The difference matters. A paradox can be practically solved while remaining conceptually alive. Consider what happens when you walk across a room. Physics tracks your velocity, measures your position, predicts your arrival time with accuracy. Mathematics models your journey as a continuous function mapping time to location. Both disciplines handle the situation beautifully. Yet Zeno's challenge persists beneath this competence. If space is infinitely divisible, your path contains infinitely many points. You somehow occupy each one. How? Saying that you do so because observation confirms it simply restates the mystery rather than explaining it. Saying that mathematical limits handle infinite series elegantly is true but does not address what it means physically to complete such a series. This gap between mathematical models and physical reality runs through all of Zeno's paradoxes. Mathematics can demonstrate that 1/2 plus 1/4 plus 1/8 and so on equals exactly 1. The proof is rigorous and satisfying. But does this mathematical truth explain how you actually traverse those infinite subdivisions of space, or does it simply show that our mathematical description of traversal remains consistent? The question sounds pedantic until you realize it points to something profound. We do not know whether our mathematical models describe reality or merely organize our observations of reality in useful ways. The arrow paradox makes this gap especially vivid. At any single instant, the arrow occupies a space equal to itself. At that instant, with zero duration, what does it mean to say the arrow moves? Calculus introduces the concept of instantaneous velocity, defined as the limit of average velocity as the time interval approaches zero. This works mathematically. You can calculate the derivative, find the velocity at any instant, predict where the arrow will be, but what is the ontological status of this instantaneous velocity? Does the arrow possess it as a real property, at that durationless moment? Or is instantaneous velocity a mathematical abstraction, useful for calculations but not corresponding to anything that exists at a single instant? Physics does not quite settle this either. Quantum mechanics introduces uncertainty relations suggesting that position and momentum cannot both be precisely determined. This seems to rescue us from the arrow paradox by denying that the arrow has a definite location and velocity simultaneously. Yet this solution comes at a cost. We must abandon classical determinism and accept fundamental limits on what can be known or what exists. The paradox forced a choice between incompatible views of reality. We solved it by changing what we believe about nature, not by showing that Zeno's logic was faulty. Modern speculation about quantized spacetime offers another possible resolution. If the Planck length represents a genuine minimum distance, space is not infinitely divisible after all. The dichotomy paradox dissolves because you cannot keep halving distances forever. You eventually reach indivisible units. Motion becomes a matter of jumping between discrete positions rather than flowing continuously. This sounds like victory over Zeno, but it introduces new paradoxes. What happens between the jumps? If space is fundamentally discrete, how do we explain phenomena that seem continuous? And why do our best mathematical models of physics rely on continuous functions if reality is actually pixelated? The persistence of these questions reveals something valuable. Unsolved problems drive intellectual progress. Zeno's paradoxes helped motivate the development of calculus, challenged mathematicians to rigorize the concept of infinity, and pushed physicists to question assumptions about space and time. Each generation that grapples with these puzzles gains new tools and insights. The paradoxes function not as obstacles to be cleared away, but as perpetual spurs to deeper thinking. A problem that yields too easily teaches little. A problem that resists solution for 25 centuries forces you to examine your most basic assumptions again and again. This is why Zeno's paradoxes appear in philosophy courses and physics departments, in books about mathematics and books about metaphysics. They occupy a rare space where abstract reasoning meets everyday experience. Walking across a room is ordinary. The impossibility of beginning that walk, once you accept Zeno's premises, is extraordinary. The paradoxes remind us that the familiar world rests on foundations we do not fully understand. Reality works, but we cannot quite explain how. Our theories succeed brilliantly at prediction, while leaving conceptual gaps. This tension between practical mastery and theoretical understanding is not a flaw. It is the human condition. Zeno's method proved as influential as his specific arguments. The reductio ad absurdum approach he pioneered became a fundamental tool in philosophy and mathematics. To show that a position is untenable, you assume it is true, and then demonstrate that it leads to contradiction or absurdity. This technique appears everywhere in later thought. Euclid used it to prove that there are infinitely many prime numbers. Medieval philosophers wielded it in theological debates. Modern logicians built formal systems on it. Every time someone says, "Suppose for the sake of argument," and then derives an unacceptable conclusion, they echo Zeno. The paradox is also established an enduring standard for philosophical problems. A good philosophical puzzle should be simple to state, impossible to dismiss, and resistant to easy answers. It should make you question assumptions you did not know you held. It should remain interesting even after you think you have solved it. Zeno's arguments meet all these criteria. A bright child can understand what the dichotomy claims. A professional philosopher cannot quite refute it to everyone's satisfaction. This accessibility, combined with depth, makes the paradoxes ideal teaching tools. They initiate newcomers into philosophy while continuing to challenge experts. Perhaps most importantly, Zeno's paradoxes remind us that ordinary experience is strange. You walk across rooms without wondering how infinitely many subdivisions can be traversed. You watch arrows fly without puzzling over what motion means at an instant. This everyday competence is remarkable precisely because it operates despite profound conceptual difficulties. The universe does not wait for philosophical clarity before proceeding. Motion happens, change occurs, plurality exists. Yet we cannot fully explain these facts in terms that survive Zenonian scrutiny. This gap need not be disturbing. It can be humbling and exhilarating in equal measure. We live in a world that works beyond our complete comprehension. Our mathematical and physical theories are spectacularly successful, yet they rest on concepts we cannot entirely make sense of. Infinity, continuity, instantaneous change, the relationship between mathematics and reality, these remain genuinely puzzling. Admitting this does not mean abandoning reason or embracing mysticism. It means recognizing that reason has uncovered mysteries, not eliminated them. Some philosophers have argued that Zeno's paradoxes are linguistic confusions or category errors, problems that vanish once we use more precise language or clearer concepts. This response misses what makes the paradoxes endure. They are not tricks or sophistry. They are genuine collisions between reasonable assumptions and unacceptable conclusions. They expose real tensions in our conceptual frameworks. Dismissing them as mere confusion is intellectually lazy. The difficult work is acknowledging their force while continuing to build better theories, all the while recognizing that those theories may harbor new paradoxes waiting to be discovered. The paradoxes that refuse to die teach us that philosophy is not simply a prelude to science, a primitive stage we outgrow once we develop better methods. Philosophy asks questions that often cannot be answered empirically or mathematically. How is motion possible? What is time? How does the continuous emerge from or reduce to the discrete? These questions inspire scientific investigation and benefit from scientific discoveries, but they retain a philosophical core that survives even our most sophisticated theories. Zeno showed that simple questions about everyday phenomena can open into bottomless depths. We are still learning how deep those depths go. The final chapter brings us full circle, back to that simple act of walking across a room, now laden with centuries of contemplation.